wonderful creative break for me. And they invited me specifically to work on this somewhat obscure topic. But this also means that this is very much still work in progress. So I apologize in advance when it's a little bit unsharp or meandering at times. And that thirdly means that I'm very grateful for feedback. Not just in the discussion now, but I'm still around for another 2.5 weeks. So please feel free to come and talk to me if you're interested. Here's my email, can contact me. And I have an office upstairs on the 4th floor, and I'm here pretty much most of the time. So yeah, I'm very happy to talk about these things more. Okay, let's get started. A tiny bit of history, which you probably know, but let's just get it out. Hugh Everett is sort of a rather obscure character, right? He wrote this dissertation in 1956-57 with John Wheeler, in which he proposed to solve the von Neumann's measurement problem. And that was the only thing he ever did in physics. He then later went to the military and became then a military contractor and never really published anything in regards to this or any other physics. So we have very little of his original words. And to make matters worse, the dissertation did not get published for quite a long time. Only a very short version of it got published in Physical Review at the time and was basically not read by anybody. It became, if you look at the citations from the first 10, 15 years, there's practically zero. But nowadays, right, it is commonly seen as the origin of what we call the many worlds interpretation of quantum mechanics. And I will get to that in a bit, how that happened. But, as I immediately want to point out, right, one striking fact is that in the whole rather lengthy dissertation, there is not a single mention of worlds or of branching or of any of that kind, right? If you read the dissertation, you will not find anything about any of that. So, and this is, what as, being somewhat dislocated between history and philosophy of science, I find the interesting point, right? The philosophical debate about the many worlds interpretation has completely ignored this dissertation. A young colleague, his name is Damon Moley at Utrecht University, is writing his dissertation on Everett. He has sort of quizzed the main participants in the contemporary philosophical debate and found that basically even the philosophers who talk about many worlds have not really ever read Everett himself. So this is what I want to address today. I want to present you, give you a short overview of sort of what I think are the main points of this dissertation. And I want to argue that it does not really introduce any specific interpretation of quantum mechanics, that it really rather introduces a formalism, an extension of von Neumann's formalism of the measurement problem, but that formalism in itself is in need of an interpretation, and that Everett gives us very little help in that regard, right? He says hardly anything about how to think about this formalism. And having done that, I want to, give you a brief outline why I don't think the many worlds interpretation is the correct interpretation of what Everett was trying to do, and give you a few other examples of how we could think about what Everett is doing. Yeah, let's start. Everett's thesis. So one thing that is, I find also again historically very striking, is that as far as I can see, Everett was the first one ever to apply Shannon's theory of information to quantum mechanics. Right? I mean, when we now think of quantum information, I've read sort of a few historical overviews of quantum information theory. They all start sometime in the 70s, and nobody ever, mentions Everett as, you know, having participated in any of that. And again, that's not surprising, right, because nobody read the dissertation, so yes, this was totally sort of, you know, this solitary work that had no consequences. But still, I want to like give you a little idea of what he was doing, especially because I think that is very important for what he thought then about what the solution to the measurement problem should be. So what he does specifically is, you know, he takes the Shannon information theory and applies it to entangled states and analyzes entanglement in terms of information theory. Right? He defines marginal and relative states of in entanglement, and you know he defines the correlation between the subsystems in an entangled state. So he does that very much sort of in the line of von Neumann's formulation of quantum mechanics. Right? He treats quantum mechanics as a theory of statistical ensembles. And very central to him is sort of the use of mixed states as a general representation of these ensembles. So he treats very much sort of the basis of his treatment is the theory of mixed states. And so, of course, the first thing, right, if you think of a mixed state as an ensemble state, right, I mean, it's very straightforward to think of, you know, how to apply information theory to that, right? And the physical side of it, of course, is that, you know, Shannon information is simply proportional to the entropy of the state. So this fact that, you know, an entangled state will always mean that the individual subsystems are in a mixed state is sort of absolutely central to his whole argument. And of course, the additional fact, right, that entanglement means that these mixed states are correlated. And, you know, the correlation measure is, you know, is well defined through information theory. And the second important point, of course, is that, you know, in an entangled state, if you now pick a specific pure state for each subsystem, then you always have a well-defined relative state in the other subsystem. And so what he does then with this sort of, you know, this rather lengthy part on information theory and quantum mechanics that I'm not going to go into any detail, he uses that to extend von Neumann's definition of measurement, right? So he defines generally measurement. You remember in von Neumann, you simply have the idea measurement means that you have an interaction between a measured system and a measuring apparatus, which is defined by the fact that if the measured system is in a pure state of some measured observable, then this will cause the measuring apparatus to go into a pure state of the measuring observable, right? And that is sort of the whole definition that von Neumann gives of measurement. So Everett generalizes that and says that any interaction that creates, one, a stable record, right? So there has to be some stability in the measuring apparatus, right? It has to preserve whatever trace the interaction left in the information in the measuring apparatus. And secondly, all that we need is not like this strict pure state definition that von Neumann used, but a more general idea that anything that increases the correlation between the measured system and the measuring apparatus is a measurement. And that means there can also be approximate measurements, right? There can be measurements that do not perfectly correlate the states of the measured system and the measuring apparatus, but only give a non-maximal entangled state. And so already for that, I think it's quite interesting because, you know, it is a substantial improvement or generalization, at least, of von Neumann says. But of course, here you have exactly the same problem that von Neumann has, right? such an interaction as defined by quantum mechanics will never give you a pure state as the outcome of the measuring process. Right? You will always end up with a superposition with the complex entangled states in which all possible measurement outcomes are present. So the question is, what do we do with that? Do we, just as von Neumann did, postulate that there must be a second physical process, right? The reduction of the wave packet, the collapse of the state, whatever you want to call it. Or do we need to modify quantum mechanics in some substantial way? Do we need to introduce hidden variables? Do we need to have nonlinear theories, collapse models, the whole plethora of proposals that have come out of that. So what Everett says is here, I have quoted you here, the original. However, we do not do justice to the theory of pure wave mechanics, right? So just unitary evolution, until we have investigated what the theory itself says about the appearance of phenomena to observers, rather than hastily concluding that the theory must be incorrect because the actual states of systems as given by the theory seem to contradict our observations. So this is his idea, right? He wants to show that it's good enough to have unitary evolution to explain the appearance to observers of like having the outcome of a definite measurement result. So first of all, question, what defines now a conscious observer here? What do we need consciousness for this? As von Neumann implied at least. What Everett says, no, we don't need anything particular, right? We need a memory, right? Because we need, as we've already said, for measurement, we need a stable record. So all we need to do is sort of equip the observer with some memory in which his subjective appearances, right? We're talking about the appearances to observers are registered as some physical trace, right? So there is some physical state or subspace of his state space that will represent the fact that the observer has perceived this or that measurement outcome. And so this is very simple, right? Observer states are simply defined by a list of memory entrances, right? So he writes that in this very simple way, right? The state vector in the simplest case is simply defined by a list of memory entries that can be added on, that are added on by each act of observation. And so in the simplest case of von Neumann measurement, that means, right, if you have a pure state of the measured observable and that interacts with the observer, then the observer will go into a state where sort of the measurement result is entered into their memory. And of course, just as in von Neumann, right, that means, so I'll spare you the more general formulation of approximate measurements. This is, let's keep it simple here. This won't change much. So if you have a superposition, then just as in von Neumann, we have just the superposition of these results, where again, we have a superposition of these observer states with these different memory entries. And now, what Everett observes is that if you just look at the observer, her marginal state, right, of the observer herself is a mixture of states, right? It's simply a mixed state of these various omega AIs. And this mixture, again, is correlated to the measured eigenstates. And he secondly observes this has to be an irreversible process because we have demanded that these memory states are stable, right? We must postulate that these are, that these cannot be erased again. So the central claim that Everett makes in his dissertation is now, since this is a mixed state, right? The observer state is a mixed state. It will always and in all situations behave like a statistical ensemble of independent states, right? This observer will just be like, a statistical ensemble of observers having observed the different outcomes of the measurement. And hence, right? The observer herself can never notice that she is not in a pure state, but in this mixture. And this is, Everett does not argue any further for that, right? He's content with saying that that is good enough, that the observer is in a mixed state, and the mixed state represents an ensemble. This is a bit problematic because, of course, quantum mechanical mixed states are not exactly the same as classical statistical ensembles, right? One fact that we here have is the so-called basis problem, which is well known in the discussion of Everett, right? That there is no, it is not necessary to analyze this mixed state of the observer in this specific state, in this specific basis of observation states, right? Why not analyze it in some totally different basis? But I think there's, you can strengthen his argument, right? We have learned a lot about decoherence since Everett wrote, and the simple answer to sort of this worry is that, we as observers are not quantum computers, right? We have a very well-defined functional basis of observation states. So that is definitely strengthening Everett's argument. But that's not what I want to talk about. This was actually part of my dissertation. If you want to look at it, that has been published. Yeah, you see that in the footnote. So the question that is much more interesting for now is the question what to make about this claim, right? That we can interpret this mixed state of the observer as a somehow statistical ensemble of observers in different states. And there, Everett is practically silent. All that he ever says in this whole dissertation is contained in one footnote, which I here show you, right? So what he says is, at this point we encounter a language difficulty. Whereas before the observation we had a single observer state, afterwards there were a number of different states for the observer, all occurring in a superposition. Each of these separate states is a state for an observer, so that we can speak of the different observers described by the different states. On the other hand, the same physical system is involved, and from this viewpoint, it is the same observer which is in different states for different elements of the superposition, i.e. has had different experiences in the separate elements of the superposition. So, yeah, maybe it is one observer in many states, maybe it is many observers in, different states. But, basically his idea is that, we can understand it so as if, the observers were, there was an ensemble of simultaneously existing observers. And obviously this is not just a language difficulty, right? This is a serious problem for metaphysics and for physics, I would say. And so this is really sort of where the interpretation debate only starts. And as I said, Everett is not much help in this further question. But let me, before I get to the questions of how to interpret what Everett is saying here, to what he shows that he can do with this idea, with this extended von Neumann model of measurement. So what he's trying to show you is that even though there is never a unique outcome of measurement, right, there is always this mixed state in the end, all the observed effects of the reduction postulate still hold. Everything acts as if the state had been collapsed to a single pure state. Because as we said, right, for each observer state, there is a single relative state of the observed system. And so to each memory state of the observer, the future physical behavior of the measured system will be just as if it was in this reduced state. Right? It will always, the observer will never be able to detect the fact that there is something else but that reduced state in the observed system. Right? So for example, that means that when the observer measures again, we'll get the same result, right? If different observers measure the same system, they will agree on their results. And, you know, Everett spends quite some time on trying to show you that, you know, if we now have a whole ensemble of identically prepared systems and do measurements on them, right, the series of measurement outcomes entered in the memory of the observer will, with measure nearly 1, reflect the Born probabilities of the measurement outcomes, right? And so this, he argues, shows you, right, you can prove the Born rule from his assumption, right? You don't need to introduce the Born rule as an independent postulate of quantum mechanics. It follows from his assumption. Now, this has again encountered a whole lengthy discussion that I will not enter now. We will, you know, this is whole different business, but I think it is also less problematic than many people think. But as I said, I will not go into that. And, you know, he also argues that, you know, you will always have, you know, the results will always obey the uncertainty principle, right? That if you measure now, you know, different non-commuting observables on one system, there's, you know, the results will, of course, vary according to the uncertainty principle. But what I wanted to spend a little bit more time on talking about is his discussion of what happens when we now observe entangled states, right? And in that, he tries to show you that, you know, all the problems that we've had with EPR, with, you know, the then not yet known Bell inequalities and their interpretation do not appear to him, right, that he can explain all of the outcomes of quantum mechanics without violating locality. So the simplest example again, right, I'm working here just with the simplest possible way. We have a maximally entangled state, right? That is like that we've written in some, like, you know, preferred basis in which it is just diagonal, and we have two observers, Alice and Bob, right, that are ready to measure each subsystem on each side. So Alice measures some observable A on that is exactly that observable, which eigenstates we have written the entangled state in, right? And so her memory states just get simply correlated with the phi I of the A side.
Quick technical remark.
Yeah.
I just got a message that you cannot hear well. I can pull this a bit
Oh.
to your just like this. Yeah.
Is this better?
Let's try it. Maybe
Yeah.
a message from that.
Let's try. Okay. So simple correlation, right? And now Bob measures some other observable, right? Some non-commuting observable on his subsystem, right? And this observable, let's call it B, has some, you know, set of eigenstates eta j, right? That we can represent in the phi basis simply as this factorized sum. And so the resulting state is now that Bob is going to be correlated to his subsystem, right, written in the basis eta j, and hence, you know, we have included these factors of the, you know, representing the basis change. So what has happened is like two simple local interactions, right? The correlation of Alice with her subsystem and Bob with his subsystem. But, you know, these are two perfectly fine local interactions. And now, of course, we want to ask, so what's the result of that all? So let's introduce LEHNER, who's outside of the laboratory and has not participated in anything yet. and he checks now on both Alice and Bob what their measurement results were, right? And that just means, again, Wegener locally interacts with both Alice and Bob and records their results again in his memory, right? And again, this is simply another simple fact of correlation, right? Nothing much changes about the state, but that Wegener now gets correlated with both ends of the entangled state. So we have in the end just one big entangled state of Alice, Bob, Wegener, and their two subsystems. But, you know, if now Wegener evaluates, right, the probabilities, right, in this Everettian sense, right, namely the measure on the total state space, right, I mean, that's basically the upshot of Everett's claim, right, that these, you know, these amplitudes simply straightforwardly give you the probabilities, then of course he gets the correct quantum mechanical predictions for the results of measurements on correlated states, right? So Bell is satisfied, and EPRs worry that we need some non-local interaction for some spooky action at a distance to get this result is resolved, right? There was no interaction that was in any way non-local here. And so I think a general interesting result beyond you know, what Everett now tries us to believe is that really this shows very clearly that, you know, the problem with locality is a problem with the reduction postulate, right? It is exactly the reduction of the state at the moment of measurement that introduces the non-locality, not the entanglement, right? As long as we look at the entanglement as just as a big mixture of locally interacting states, then everything is perfectly fine. So, and I think this is an important strength of what von Neumann is, what Everett is proposing, right? That, you know, bracketing this question of how to make sense of what he says, he at least gives us this hope, right, that there is a way of harmonizing locality with the measurement of entangled states. And the question is how we can pan that out, right? So let me just summarize this very quickly, right? What Everett is, what the strength, what really is interesting about what he's proposing is, one, that he gives us a very general account of measurement and observation that is sort of, you know, very solidly rooted in quantum mechanics and, you know, harmonizes perfectly well with all we know about quantum mechanics. He gives us a account of approximate measurement, which is actually very realistic. He avoids, or claims he can avoid, this whole problematic idea of the state reduction, the collapse of the wave packet. He gives us, I think, substantial, you know, plausible argument why it is that observers in mixed states will not be aware of that fact. And I think that is really the most important point. He gives us this idea that we can explain measurements on entangled states without invoking, you know, any non-local reduction process. But of course, that all hinges on the question if we can make sense of this mixed state of the observer, that this does not totally fly in the face of, you know, what we know about physics otherwise. And so let's turn to that now. I should a little bit look at the time. That I'm, what's the time frame exactly?
Like half an hour. You can
Yeah.
go on at least like 15 more minutes.
Mm-hmm. Okay. Okay, I'll try to be compact here. So, as I already said, right, Everett only published this very short version that was, you know, in itself rather incomprehensible and was not really discussed by anybody. And so the rest of the world really only came to notice what he, Everett, in an article that Bryce DeWitt published in 1970 in Physics Today, which you probably know is a popular science journal, right? And so this article was also rather popularly written. In this article, right, he did something very different of what Everett had done in his dissertation. He gave you a very clear picture of what this all means, right? And so we don't have just this sort of, somewhat unclear idea of there may or may not be many observers, but DeWitt says very clearly there is many worlds. So he really creates this idea of the many worlds interpretation. He introduces this idea of branching of worlds, and I'll give you a quote to show you how much different that is from what Everett has been saying. This universe is constantly splitting into a stupendous number of branches, all resulting from the measurement-like interactions between its myriads of components. Moreover, every quantum transition taking place on every star in every galaxy in every remote corner of the universe is splitting our local world on Earth into myriads of copies of itself. Right? So I hope I can impress on you that this is quite different from what Everett wrote. Right, and especially, and I'll get to that in a second. Right, this is of course now we have non-locality with a vengeance. So the idea that Bryce DeWitt had here is, right, you can understand Everett with this idea of there is this one big wave function of the whole universe, right? This one big, hugely entangled state of the whole universe in totality. And this, just as Everett's mixed state for the observer may describe many observers, this state of the universe now describes this, infinity of parallel worlds that all exist besides each other. So the many is not just a language difficulty or a way of speaking anymore, right? Now we have a robust metaphysical picture, right, of a multitude of worlds existing in parallel, or branching, of course. And branching itself is sort of this primary process, right, that is, a physical process that happens non-locally through the whole universe. So this in itself is, of course, physically already rather problematic. But what I think is the more fundamental problem is that this whole assumption of a wave function of the universe is not just physically, but also philosophically very problematic. And the first thing we can argue against that is that it's in principle unobservable, right? We have defined what observation is, right? Observation is the correlation with the observed system that will never get us any closer to any knowledge about the total wave function, right? It will actually, hide the. We knew before more about the total wave function than we know after observation, right? It will get us away in information theoretic terms. So this wave function of the universe is this purely metaphysical construct that has nothing to do with any of our actual acts of observation. So let's try Everett another way, right? Let's go the opposite way. Let's start with empirical reality, right? If we want to say, right, that Everett is consistent with what we know about single outcomes of measurements, right, what this ensemble of observer states describes is merely a range of possibilities of measurement outcomes. Right? And if we want to say that that is just what quantum mechanics is, then that means that quantum mechanics always is just about possibilities, right? It just simply never tells us the actual facts. It always only tells us, as Jordan says, transition amplitudes, right? Probabilities of having a result if you had another previous result. And that in itself, right, is not so different from what we've done in physics before, right? Also in classical mechanics, right? Classical mechanics never gives us a single trajectory. It never tells us how a certain particle will move unless we have already specified boundary conditions, right? Initial, final conditions, or something like that, right? So you can say, in that regard, quantum mechanics is not so different from classical mechanics. We always need additional information that is not included in the formalism to describe a specific empirical reality. Only that, of course, in quantum mechanics, every single observation will give you new boundary conditions, right? In classical mechanics, once you fix them, they're fixed for all and good. But that, in turn, just means that quantum mechanics is an indeterministic theory as opposed to classical mechanics. So if you look at Everett that way, right, then he really doesn't say much different from what, you know, the Copenhagen orthodoxy had been saying all along, or certainly at least some directions, right? This idea of Copenhagen orthodoxy is very problematic, right, because they didn't agree on many things. But so, you know, to be a bit more specific, right, it is sort of very much sort of what the modern information theoretic approach says, right? Quantum mechanics just gives us this general formalism about probabilities, right? But, you know, the actual fact of measurement is a raw data, yeah, that, you know, quantum mechanics itself cannot explain. Or we could go on, right, and say whatever it shows us is that we need another physical fact that actually physically explains why we have this or that outcome of the measurement, right? We need to need to have more physics here. And so then it's just sort of this general framework for, you know, any, you know, hidden variable or collapse theory that you might want to think of, right? You can argue that, you know, the Broglie-Bohm theory is basically Everett just with a finger of God pointing on one specific trajectory of, you know, observations through history, right? While in Everett you have again just the totality of all possible trajectories of hidden variables. You know, what the Broglie-Bohm stipulate is that there is one of these that is actually real. So what I want to argue here is that this general formalism that Everett introduced is very much compatible with, you know, basically any interpretation you can think of. Right? What you want to make of it really just essentially depends on how you want to interpret this mixture of observer state that the formalism gives you. And sort of the difference really is, what do we call reality in, you know, this mixed state of observation outcomes? And now, of course, you could say, as a physicist, I don't care about this. This is just a matter for philosophers to worry about, right? Reality is not something that I need to worry about when I do any theoretical or experimental work in physics. But I don't think this is quite correct, right? And this is sort of my argument against, you know, the mainstream of modern information theoretical approaches to the philosophy of quantum mechanics, right? I think we do in physics in general make and need to make this distinction between objective matters of fact and their theoretical description. And that is simply, you know, an assignment of reality, right? So when in a local gauge theory, I distinguish, right, between gauge independent objective fact and its various coordinate or gauge dependent descriptions, right? I'm doing exactly that, right? I'm claiming that there's in my theory something that is more real than the various descriptions I give theoretically. And so I think also for physics, this is a relevant and important question: what is real here? But again, right, I am very much sympathetic to this idea that we need an empirical reality here. We don't need a wave function of the universe that nobody can ever see. And so I think this interpretation debate is relevant. And as you can immediately see, right, when we think of these different interpretations as different interpretations of Everett, right, they do make a difference in the physical structure of the theory, right? They will give you different answers, especially to this interesting issue of locality, right? The moment you do introduce hidden variables or collapses, right, you will not have a local interaction anymore in the observation of entangled states. You will need explicit non-locality, right? That is clear and understood, and if you've ever read all this literature about EPR and the Bell inequalities, and so there's always like these, basically two assumptions, right? One is about locality and one is about realism, right? Variously defined, but this is always sort of the basic assumptions that get you into conflict with quantum mechanics. So it's clear, right, if we are too straightforwardly empirically realist, right, if we just want to say our observations reveal a pre-existing reality about the physical state of the entangled system, then we will have a problem with locality. And so, of course, the adherents of these interpretations argue then, so what? Let's go, locality just has to go. Entanglement just shows us that the world is non-local in this very fundamental way. But, again, I think this is a very problematic move. It's not only at odds with sort of practically all of our, theoretical and experimental practice in physics, right? But especially, and that I cannot stress enough, right? It's not in any way supported by the phenomena, right? We have the no signaling theorem, right? We know that this spooky action at the distance cannot ever have any observable effects. So if our theory says that there is spooky action at a distance, then to me that just shows that there's something wrong with the theory, right? It does not reflect the phenomena. So the interesting question, right, Everett gives us this hint that there might be a perfectly nicely local explanation of measurement of entanglement. Can we flesh that out? Can we give a local interpretation of Everett without totally violating our, ideas of empirical realism? And so let me give you, as a last step, a brief sketch of how I think we can think about Everett doing both of that, right? Preserving locality and preserving some sense of empirical reality. So I think, something has to give, obviously, right? But notice that, when we talk about realism in these, EPR type or, Bell inequality type considerations, we always have this very straightforward, let's call it naive realism, right? That observations reveal an objectively existing fact, right? They reveal something that was already there in nature, and we just learn about it, right? But we know very well from physics that there's plenty of measurements that are very good physical measurements that, don't reveal observer-independent facts, but facts relative to observers, right? We measure velocity always relative to something, usually relative to us, right? Energy is not ever absolutely defined, it's always relative to something. So these relative states of Everett can just be very well considered as something like that, right? They are relative to a specific observer's state. So what does that mean? Let's go back to my previous story about LEHNER and his friends, right? In this big entangled state that I've shown you of LEHNER and the friends, right? Let's assume, right, Alice and Bob have previously agreed on what they measure, right? So they can both know the total state, right? They know what the entanglement is, how Bob is entangled with the state, and how Alice is entangled with the state. And so they both know what the other's relative state relative to their observation result is. So Alice has observed some specific value, AI, right? And so she can say Bob's relative state to that, given that she knows what the sort of, the theoretical prediction of the total entangled state is this superposition, right? It's a superposition of all of Bob's measurement outcomes with the appropriate factors. And equivalently, right, Bob can attribute to Alice an entangled state of all of her measurement outcomes. And LEHNER, well, it actually doesn't matter, right? Before he asked them simply the total entangled state as his relative state. Can also say that what happens after he asked them, of course, then it's really only the pure state anymore. And interestingly, I've just realized recently, it's pity that CHRISTOPH couldn't come today, that he's actually written a paper analyzing exactly that situation, right? And it's called, as you see here, a no-go theorem for observer-independent facts, right? Coming to exactly this conclusion, right? That this forces us to assume that, there is no objective observer-independent facts in this situation, but only these relative states. But these relative states, of course, mean they do not give you a single, simple reality, right? Alice cannot say that Bob has perceived a specific result, and Bob cannot say that Alice has perceived a specific result. They just express, again, like this range of possibilities for their possible future observations. But we can say they don't contradict each other, right? If we accept that empirical reality is always relative to a specific observer state, then this is just, three perfectly good descriptions of, a total situation that is not like, can only be represented in these relative states. And what that means is that reality here is not this like objective fact out there, right? But is what philosophers call, or philosophers' language call, an indexical, right? It always is relative to your local position in the whole network of the universe. And, a very simple example of that from physics, right, is the idea that in general relativity, right, we have this huge space-time continuum, right, and the present can always only defined as this indexical, right? There's nothing in general relativity that ever implies, where you are in the space-time, right? This is something that is sort of always relative to the standpoint of you in space-time. But, of course, if we want to talk that way, right, if we want to think that way, then we have to accept that these ranges of possibilities have a physical existence just like the totality of space-time, right? We cannot think of, this is just a manner of speaking or a manner of thinking about the world, right? These possibilities then do have to somehow physically exist, like in space-time continuum, all points on space-time exist. So we can call this a theoretical existence, right? We can be sort of, be somewhat metaphysically non-committed about it, but as far as the physics goes, right, this means they're there just like the totality of space-time is there. Right? So for Alice, all the outcomes for Bob's measurement are equivalently real, and there cannot be an objective fact which outcome Bob has observed, and vice versa, right? And sort of, you know, just as if you think about the double slit experiment, you say that, yeah, the electron or the photon or whatever particle has to have gone through both slits, right? Otherwise, the interference could not have happened. And, you know, of course, that is a challenge to common sense, right? That is what makes Everett's interpretation really different from, you know, other interpretations. But, you know, on the other hand, right, nobody has ever said that quantum mechanics was not a challenge to common sense. So I don't think it is, you know, that in itself is a disqualification. And, you know, what I want to stress is this all does not mean we cannot have a stable sense of empirical reality, right? It looks a bit different than what we were used to, right? But it is perfectly robust, right? And that is Everett's argument, right? We will all agree on empirical reality. We will not wander into different worlds, or, you know, as we were on time travel, right? Physics, you know, will still behave exactly as it behaved in the time of Bohr and Einstein, right? There will not be any, like, you know, weird surprises here. Just, you know, as general relativity does not imply that we don't have a present. Okay, so let me come to an end here. Yeah, this footnote says, right, that, you know, just besides physics, right, modal realism, you know, this assumption that possibilities physically exist solves us a lot of problems that philosophers have worried about for a long time. So it's also attractive on other counts, but that's a different story. So just one objection, of course, to that, you could say that, you know, I've now compared, right, sort of the existence of the totality of space-time, even though we always only experience the present, with the existence of a totality of possibilities, even though we always only exist one single empirical reality. And you can say, this is different in general relativity, right? If I wait long enough, right, I will see the rest of space-time too. So, you know, philosophers call that it will be empirically accessible eventually. But, you know, again, I would argue, this just expresses the fact that general relativity is a deterministic theory, right? So yes, what we see now already determines everything we will ever see in the future, whereas quantum mechanics is a radically indeterministic theory. And to turn this argument around, right, if we want to ever have the hope to unify this idea of space-time, of a block universe in general relativity, with the indeterminism of quantum mechanics, then it has to be that possibilities do physically exist. Because otherwise, right, the block universe already would enforce determinism, right? There cannot be an indeterministic block universe if possibilities do not exist in this block universe. But that's a side point. So let me finish here. I'm going too long. So the wave function of the universe is, you know, I would argue what Kant called the noumenon, right? Something that we can think of in our theoretical fantasy, but which has no empirical impact ever, right? And so with that wave function of the universe, so are the many worlds, right? These are ways sort of to illustrate the idea of the existence of possibilities, but it's a very misleading way of illustrating this idea, and has led to all kinds of very misguided discussions about the interpretation. But on the other hand, Everett was right, right? There is a language problem here, right? If you want to say that possibilities exist, right? This is very much at odds with how we have, like, for the last few million years talked about the world. We do need a new language to really distinguish empirical reality from this totality of possibilities. And that really would be a job for the philosophers, right, which so far they've completely failed at. So let's leave it at that, right? What Everett said, right, in his dissertation, right, that was his central claim, right, that what he was doing, his account of measurement, could save the phenomena. And so I think that we should take seriously, right? We should look at Everett's proposal as theory of the phenomena and not just some metaphysical speculation about, you know, the wave function of the universe and many worlds. But, you know, it makes some substantial and strong claims, right? It does demand that we accept the existence of possibilities as physical facts, right? And it demands to accept that empirical reality is not an absolute, right? There is no objective fact about the world independent of our observations, but is always relative to the observers. But with these assumptions, right, it really can give us a coherent account of the measurement process. And again, right, this is, I think, one of its main highlights. It can do that without needing spooky action at a distance. Okay, that's it. Thank you. Sorry for being so long.
Okay, thanks very much for the great talk. I hope this microphone is working. Other questions? Yes.
Hi, thanks for this excellent talk. I have a question about the formalism that Everett uses and introduces. So it seems that really a key element is this notion of memory and of persistent memory of these outcomes. So was he thinking of that, as the notation suggests a little bit, that they would be part of the state in the Hilbert space, as encoded through different states of the Hilbert space, or something outside of that?
Yeah. No, definitely very explicitly, right, as, you know, in general, of course, not a single state, you know, but, you know, in the simplest case, right, we can say, right, the observer is simply a physical system with a Hilbert space, and, you know, this memory means like some specific state or subspace of that Hilbert space. Yeah. And this way, right, he always writes it as a quantum mechanical state.
I guess one worry one might have with that is that, I mean, there could be situations where different past measurement outcomes coincide in all future predictions, right? It could happen that, I mean, there are certain measurement outcomes, and there's a different set of measurement outcomes, but they are arranged in such a way that any future measurement that this observer can do will have the same outcomes the same outcome probability, in both situations. So then one would usually want to say, okay, so then we should say that these states have to be the same, right? So does Everett kind of go into this problem, or consider this?
So you mean we have like different subjective impressions, but they're physical, you know, the meaning, what they say about the world is exactly the same?
I'm only referring to the meaning with respect to future measurements. I mean, let's say that there are measurements A, B, C in the past, and now it turns out that the observer has observed certain outcome in each of them, and now in another possibility, let's say in the second measurement B, he observed a different outcome, but it turns out they're arranged in such a way that the predictions for future measurements are the same for these two possibilities. So then one could argue that the state in the Hilbert space should be the same, or maybe up to a phase or something. So that looks like it could be a problem, and that
I don't see why it would be a problem, right? I mean, basically, I mean, you know, the central point is, right, I mean, what he says, different observer states, right, different impressions, right, by the definition of a measurement being a good measurement, are correlated to different relative states, right? So there's also a physical difference in the world. And so in principle, I would say that, you know, this difference could always be revealed by future measurements, right? it could not, in a good measurement, it could not be, right, that the observer, and then it simply would not be a measurement in Everett's sense if the observer had different memory entries, but they would refer to the same state of the world, right? So of course a perfectly plausible physical interaction, but in psychology we would rather call that an illusion than a measurement, right? So I think there should, once it's a measurement or an observation in Everett's sense, there should always be a relevant difference in the world, and so that should always be, in principle, be possible to reveal in future measurements.
Okay. Yeah, it's not quite clear to me how, because I mean one could imagine that I'm doing certain measurements, and for two different sets of outcomes, the predictions for future measurements coincide for any future measurement. Like if in a subsequent measurement I destroy something that I observed, and then it's irrelevant if it was.
Well, that can of course always happen, yeah, but that's not a problem, right? I mean, that is, and that he actually explicitly talks about, right? That of course, if I measure the same system again, right, I lose the information, right? Then my previous memory entry becomes simply irrelevant, right? Because I have a new correlation between the observed system and the observer. So what was in the previous interaction simply does not say anything about the world anymore. That can of course be.
So in that case, it would be the same state, so to speak, in the Hilbert space with respect to future measurements.
No, I mean, that's the thing, right? He does assume that the observer states are independently defined, right? They're not just defined by reference to what's out there, right? They're defined by the subjective impression, right? I have seen this or this result, right? The pointer was standing there or so. So totally independent whether the pointer was there, right? And I mean, this is exactly the idea of approximate measurement, right? I can be wrong about that, right? I can be misguided because my interaction was not perfect, right? I do not really know that. So, he definitely needs to assume that there is an independent definition of these subjective impressions that is not just defined by the referent.
Okay, yeah. I still think that maybe that points to a kind of extension of the usual Hilbert space point of view, but okay. It's,
I mean, it is simply, I mean, talking about human observers in terms of a Hilbert space is definitely a substantial assumption, right? And people, Bohr would say, and Bohr did say, right? I mean, there's this famous story that poor Everett got sent to Copenhagen to defend his thesis to Bohr and Rosenfeld, and they hated it, of course. He was like, basically kicked out of there in shame. So yeah, of course, somebody like Bohr would heavily protest against this idea that we can express a human conscious observer by a Hilbert space, right? So yes, there is a very substantial assumption of physicalism here, but if you are a physicalist, then I think it's not an implausible assumption, right? I mean, that's definitely it's an assumption, no doubt.
Okay, so what about the speed of life? Okay, speed of light. I mean, is it empirical reality or absolute reality? I mean, speed of light.
Well,
what's your opinion?
Of course, that's an empirical reality, right? We can very easily measure that, right? And I mean that even for the wildest many worlds theorists, that will not vary among worlds, right? So I mean, I don't see what the problem is there.
Okay, because common sense is it's observer independent for the speed of light. So
what is independent of the?
I mean, the speed of light is observer independent. So it's absolute.
No, I mean, this does not mean, right, that there are no observer independent facts ever, right? Of course, there is theoretical invariance, right? I mean, it's just like in gauge theory, right? Of course, there is facts about the world that are completely observer independent. Only certain facts are observer dependent, right? So that's obviously yes.
Okay.
Speed of light is no problem.
So, so this seems like a completely sane view that I could subscribe very easily to, right? But the question is more a sociological one. Where are all the Copenhagenish Everettians actually in the philosophical landscape?
Well,
like, because usually what you see as a motivation for being an Everettian is like, oh, I want to be a realist. I want to know what's actually the case in an observer-independent way, which is this kind of universal wave function. Then you can tell the story, this is what's really the case, and then you're sort of done, right? But this paints a very different picture. That's, but is this something that would be defended by some philosophers by now? Or is this like, what would David Wallace say to this?
I mean, in the end, I haven't talked much to David Wallace about it. I've talked to Simon Saunders about it quite a bit. And he is, in the end, even though he is not unsympathetic to my way of looking at it, right? But you know, I agree when you know, in his writing, it doesn't sound quite that way. And I think that is this, you know, unfortunate historical fact that the whole discussion got sort of framed by this many worlds picture, and that's just how people talk now. And so it is actually, this way of talking makes it difficult, because I mean, that is definitely something that Simon also agrees on, that sort of, you know, the general perception of Everett is misguided and is sort of skewed to this, like, you know, you know, naively realistic perspective. It's just, you know, I think I'm sort of the soul crier in the desert that says, you know, that means we have to really change how we talk about Everett from the start on, right? I think there I'm pretty alone.
Okay, any further questions? If not, then let's thank the speaker again for the great talk.
Thank you.